All right, so you're not going to have to write anything for a while, so just sit back and listen. So about vector spaces. So vector spaces are a definition. So they're going to have all of these 10 things satisfied. I like to think of it as like a game. A game we're playing is we can call something a vector space if it does all of these 10 things. We call the elements in the vector space a vector. And we're going to find out that they make a lot of sense, and they do what we've been doing with vectors. So we're going to find that vectors, like here, the set of vectors in V2 are a vector space. The set of vectors in V3 are a vector space. So a lot of it's going to make sense, and then I'm going to show you when it doesn't turn out to be a vector space or a subspace. So you can, if you take two things and that are in U, V, and W are in the space, our vectors already in there, you add them together, it stays in there. This is going to be something we call closed under addition. You don't need to write that down. It'll be coming up soon. So if we take two things and add them, they stay in the vector space. All right, if I take the two things that are in the vector space already, it doesn't matter what order I add them. I can group them differently to add them. A 0 is in the vector space, where if I take a vector that's in the space and I add the 0 vector, I stay with just the same vector. If I have a vector u in the vector space, negative u is also in the vector space, and so what happens is that u and negative u make 0, the 0 vector. A constant, a scalar, and scalar is always a real number. Scalars are always real numbers, is in the vector space. I can take c multiplied times u and v added and distribute the c. I can take two scalars added together and then multiply it times u, or I can distribute the c and the d. I can have two constants out here in front, and I can keep them separate, or I can multiply them together and then multiply them times the u. And if I multiply the number 1 times the vector u, I get u. Okay, so these are just examples of things that are vector spaces, and you're going to think, yeah, they do all these basic things. So any Rn, specifically R2 or R3, this set of vectors is a vector space. So I'm not ever going to ask you to show me all 10 things. We'll get to that in a second, but these things, Rn, R2, R3, they do satisfy all 10 criteria to be a vector space. The set of 2 by 2 matrices make a vector space. And think about how we can add them. There's a negative, there's a 0, there's a 1. All the criteria are satisfied. The set of m by n matrices, it doesn't need to just be square or 2 by 2 matrices. They are all vector spaces. And then we have the set of real valued functions. So real valued functions like ax1 plus bx2, x to the 1 power, sorry, I meant x to the 1 power, plus c bx squared plus cx cubed, and then, anyway, so things like this, they satisfy all the criteria to be a vector space. This is one we're going to deal with a lot. We're going to deal more with polynomial functions. So polynomial functions, meaning you've got these constants, a's, in front of the variable t to the 0, t to the 1, t squared, t to the n. And so these are polynomials, so the n's are always bigger than or equal to 0, right? The exponent on the t. And then the coefficients, the a's, they're all real numbers. And the variable t can be real numbers. Okay, so the degree of the polynomial, the degree of p, sorry, this should be capitalized because it's a vector. So I'll put capital and I'll put a p hat on top of it. This vector p, the highest power of t, that's the degree. So it could be t cubed, and that would be degree 3. The 0, if there is a polynomial that has a number there that's not equal to 0, has degree 0, and the 0 polynomial is just the 0, right? It's just the numbers. Oops, there's no hat there, just the number 0, right? That's the 0 polynomial. So this is called degree 0. And if all the coefficients are 0, this is called the 0 polynomial. So this right here. Okay, we'll be dealing lots with this, so don't worry about not absorbing it all at the moment. So what we are going to do, this is our to-do list. What we are going to need to do is to show something is a subspace. And so subsets, part of a vector space, they're going to be called vector spaces. And we can show that we just need to show 3 things. So 1, 2, 3, A, B, C, to show it's a subspace of an already established vector space. So the things you know that we're already familiar with, polynomials, matrices, so nothing too weird. We're gonna, if we know that that's already an established subspace, we're gonna pick up a established vector space. Something we know is an established vector space, like this V3 or 2x2 matrices or polynomials. We'll be picking a subspace of that and asking to show if it's if it is actually a subspace. And to be a subspace, these are the 3 things I need to show. There is a 0 vector. If I take 2 things that are already in the subspace, that you add them together, they stay in the subspace, and that's called closed under addition. And if I take a vector that's in the subspace, and if I multiply it by a scalar r, or scalar c, that's a real number, then c is also in the vector space. So that's called closed under multiplication. All right, so let's do some. So for example, if I've got these 2 vectors here, and h is equal to the span of those 3 vectors. I guess I forgot to put the question here. Show this is a subspace. Okay, to show it's a subspace, I need to show these 3 things. Is there a 0 vector? Yes. So this should be 0 vector. The 0 vector is 0 times that vector 1 and 0 times the vector 2. So this 0 vector is in the subspace. Check. Got number 1 satisfied. Okay, number 2. Is it closed under addition? If I take 2 different vectors, a u and a w, and if this vector u is in the h already, which they have to be, then that means there's 2 numbers in front of the v1 and v2. And if w is in h, that means there's got to be 2 numbers, a c and a d, in front of the 2 vectors. So if I take 2 things that are already in w, right? So u and w are already in h. This little just means in, right? If I take 2 vectors that are in h, if I add them together, do I stay in h? I do, right? Because I add these 2 together, put the number in front, add these 2 together, put the number in front. Yes. So it is closed under addition. All right, so to be closed under scalar multiplication, if I take a vector u that's in h, if I multiply it by a constant or real number c, do I stay in h? Yes. This is still in h, so that means it is closed under scalar multiplication. Okay, so let me just recap a little bit again. So we'll be given something that we already know is a vector space. So establish these kinds of things that we're used to dealing with, follow these 10 rules. So what we will be given is we'll be given parts of something. So here they're just saying v1 and v2 are v in some v. The span of those 2 things, does this turn out to be a subspace? So I show the 1, 2, 3 criteria are satisfied, and then I can say therefore subspace. All right, so let's look at some more exercises or examples to find out if they are subspaces. So show these part of vector spaces satisfy the 3 criteria. All right, so this is the main vector space I'm in. Determine if H is a subspace of this vector space if H has the following criteria. So it says, okay, if you take a U and a V, When I add them together, oh, look at this weird rule. So it's a different game. And look at this weird rule. When I multiply by a constant, it turns negative in there. Okay, so it's just a different game to play. It's like someone's changing the rules. Okay, first, is there a zero vector? Yes, because I can put 0 and 0 in there. So there is a zero vector. All right, and because I'm allowed to let u1 and u2 be equal to 0. Is it closed under addition? So taking two things that are already in my vector space, in my H, my subspace, if I add them together, do I stay in the vector space? Yes, even with this weird rule of addition, I add them together, I stay in R2 and in this specific subspace. So third thing, if I have a vector and if I multiply it times a constant, does it stay in the subspace? Yes, I add them, or I multiply by the negative, it just stays in the subspace, so it satisfies the criteria. All right, let's look at when something does not satisfy the criteria. So here's a subspace that I want to see. Is this a subspace? So the question is up here. Determine whether they are subspaces. So looking at this matrices of this form, so giving you a specific format, is it true that it will satisfy the three criteria? And I'm just using regular matrix addition, regular multiplication. All right, so is there a zero vector? Well, I could let A and B be equal to 0, but the 1s are still there. So there is no zero vector. So if this was a problem of yours and you wrote this, you could be done. I'm going to go and show the other parts so you have an understanding of it. But if you're showing one of the criteria doesn't work, then you can see therefore not a subspace, and you can be done. Okay. So I'll just put, or we could look at criteria number 2. If I take two vectors, right, I'd call them vectors because they're elements of this vector space. If I take two things that are in this subspace and I add them together, does this look like it fits in matrices of this form? No, it is not, because the matrices of this form have 1s here and this matrix has a 2. So it is not in the vector space. All right. If I had take a vector, a 2 by 2 matrix looks like this, and I multiply it times C, I get this. This is not in the space either. So none of the criteria work, right? You could have picked any one of those three things. Any one of those, you would not have to show them all, but I just wanted to go through it so you understood. All right, let me stop here and I'll continue on.